Y21 diffraction. In the previous class, we studied the interference due to the two light sources passing through two tiny apertures when they arrive at a point on a screen. And today, we consider the interference pattern due to a diffraction of light passing through a finite width of aperture. Now we have an aperture of width A. So we choose the x-axis here, the origin is here, and a point inside an aperture is chosen to be Q. And the source runs from 0 to A. And we divide into many tiny pieces, and we'd like to add all of the contributions of the x from 0 to A to contribute to the electric field at point P on a screen. This diagram is a kind of exaggeration. Actually, capital D, the distance between the aperture and the screen, is very large in comparison with the width A. The electric field is then perpendicular to the straight line that connects the source and a point on the screen. Sure, there is a magnetic field too, but we don't have to worry too much about that because the magnetic field is completely determined once you compute the electric field. So we focus on the adding all of the partial contribution to the electric field due to a tiny piece of an aperture. To find a resultant electric field that has the same dimension as the original electric field with the amplitude E0, we divide the contribution by the width A. For example, if the electric field is just constant, then your integral is just 1 to that does not modify the original electric field. Okay. In order to sum all of the contributions of partial aperture that makes a full aperture, we compute the electric field partial contribution. Overall factor is the original amplitude, and there should be a phase difference. We remember the phase difference between the two contributions for a two aperture problem was we had the distance d between the two apertures, and the path length difference, this part, should be computed by multiplying sine theta to the distance d. So this d sine theta was the path length difference. And once you know the path length difference, then you divide this one by the wavelength of the monochromatic wave. In here, this d becomes a variable x that runs from 0 to a. So there is no big difference between the analysis of a single aperture diffraction and two aperture diffraction, double slit experiment. So exponential has an argument. We have a common factor, kx minus omega t, that determines the distance between the upper edge of an aperture to the point P. We remember this P and this P, these two P's are actually the same in the limit as a capital D, the perpendicular distance between the aperture and the screen is very, very large. So what we have to do is, because this k dot x minus omega t is actually depending on the distance d, and that is fixed, so kd, something like that, and omega t is common to any point. So that will be averaged out at the end of the calculation. Our main concern is the dependence of the phase on the position of a partial aperture at point Q. And this x dependence appears to be phi multiplied by x over a, as we have already explained. This d is to be replaced with x, then we can determine this. So phase difference is now determined as x sine theta divided by the wavelength lambda. Now, what we have to do is just integrate all of the partial contribution throughout the region where x is in the range 0 to a. For any case where f of theta is a cosine, sine, or exponential, we always have this kind of common factor, and the remaining piece is the same. You can do it by yourself by integration. Okay, so what we have found is the shift in the overall phase in the amplitude, and we have an additional factor that is a sine half of phi divided by half of phi. Okay, in conclusion, if we square this electric field, then we will find the ratio and divide this one by the central value at theta equals 0. When you substitute theta equals 0, you will find that phi equals 0. Okay, at the central point on the screen, you have an aperture. We have a point P at the center. Then you will find you have this value should be 1 because the central value is at theta equals 0. By definition, if you substitute theta equals 0, left-hand side should be 1. Okay, why don't we substitute theta of phi equals 0? That corresponds to theta equals 0. The denominator becomes 0, so we cannot directly substitute phi, either phi or theta equals 0. Instead, we can take the limit as phi goes to 0. You find both of them, numerator and denominator, vanishes as phi goes to 0. And you had better apply L'Hopital's theorem. And actually that value is exactly as 1. You know, sine x over x, limit x goes to 0 is the same as the first order derivative. And this is a cosine. This is 1. Limit x goes to 0. Cosine equals 1. So this is called the sinc function. Sinc x, sine x over x. This is a very important physical function. You will find in the ratio of the intensity that is proportional to the electric field squared is sinc function squared. If you square the sinc function, still in the limit phi goes to 0, the ratio is exactly 1. Except that as you vary phi that is defined by this one, you will find there are zeros. All of the zeros are called local minima. Each minimum is placed where this guy is what? This sine, this one is 0. That means 1/2 of phi equals n pi, where n is not equal to 0. Because we know when n equals 0, this whole value approaches 1 instead of 0. So this is a method to find out the place where minimum point appears. And as you can see, the denominator, numerator is always localized between 0 and 1 after square. However, the denominator keeps increasing. It keeps increasing as phi increases. Therefore, the intensity decreases strictly as you leave from the central point of the screen to far away. That's quite important. So there is a sharp peak at the center. And then, even though there is a fringe, bright, dark repetition, the global shape decays very, very rapidly. So central part is very bright, and as you go far away, the brightness decreases, becomes dark, even though there is a repeated fringes. This is a three-dimensional plot showing the dependence on the relative ratio of the width of the aperture and the wavelength. As you can see here, A over lambda is 0.5 and is 20. This shows for a given wavelength, this aperture is very tiny, just 1/2 of the wavelength, and aperture is very large. As you can see, as aperture becomes tiny, the diffraction pattern is very broad. So light wave passing through a very tiny aperture propagates its brightness is very broadly distributed. So wavelength is fixed and A is very tiny. Your fringe is just a single fringe. This central part is magnified to a wide range. As A increases in this direction, you can see the brightness drops very rapidly, and then there's a tiny bumps. So you have to be able to compare the pattern. This blue pattern shows a big aperture, and this wide spectrum, and there is no fringe, no wiggly behavior. This one very tiny a relative to the wavelengths. So if you cut this three-dimensional diagram with a knife, then you will find the following plots. So you can see A is comparable to lambda. This bump is very wide, and you don't see a wiggly behavior. But as you increase the diameter of an aperture, you will find the wiggly behavior. So bright, dark, bright central part is always 1. Okay? And as you increase the width of the aperture, then the fringe pattern appears repeatedly with a narrow width. Okay, so there are some numerical values. When you substitute explicit value for this formula, you will find numerical values for the relative intensities. So in fact, if you find the intensity distribution, this one is a very ideal case using two slits shown like that. You cut here and there and cut it off, and this distance d. So light comes in here and passes through, and you will find this kind of diffraction pattern. What happens if you change the shape as a circle instead of this bar, something like that? So if the aperture is a circle, then the calculation is much more involved. And let me show you the final result only. There is a Bessel function. This J is called the Bessel function, and your final result depends on the Bessel function divided by x. And again, as x goes to 0, this value becomes exact 1, and similar to sinc function. And your final result should be the square of this. So actual diagram for relative intensity should be something like that. Increase and 0, increase 0. So it will show a wiggly behavior in such a manner. There is a numerical value of this, the zeros of this function, and that are determined numerically like that. And you don't have to worry too much about that. Effectively, after detailed calculation, you will find is a kind of 1.22 lambda over d. Arcsine will be the angle, estimated angle of the first minimum. Where is the first minimum? This is the first minimum. So there is no way to avoid this kind of a spread of light once a light passes through a tiny hole. So it is a natural consequence we cannot avoid. So in any case, when you take picture using the camera, then you will find a diffraction. You cannot avoid diffraction. So due to a diffraction, if you take a picture of something that is very far away, then you will find you sometimes you cannot distinguish the two distinct objects due to the diffraction of the light. So that is usually parameterized by this diffraction pattern after passing through a circular aperture. So using this formula showing the first minimum of the diffraction pattern to the general case, we say theta r is the angular position of the first minimum due to a diffraction pattern coming through a circular aperture. So this is called the Rayleigh's criterion for resolvability. So if your picture is fully resolved, then you can distinguish the intensities, and the picture in this picture, just like a tomography, you can find these two objects are distinguished. But in here, you cannot say for sure whether it is a single object or two distinct objects. This is absolutely impossible to distinguish the two objects. This is basically due to the diffraction of light that travels very far away from some place. Why don't we extend our result to the case of double slit experiment? In the previous class, we minimized this size of each aperture, and we treat each contribution to be uniform of the same phase. However, we can apply the same method to compute the interference pattern of the light passing through a single sizable aperture. We do the same job with the two slits. The same is true, except that we have identical apertures of size A, and they are separated by a distance d. Then there are two scales, A and D. And usually we like to consider the case D is greater than A, and usually much greater than A. And both the D and A are much smaller than the perpendicular distance capital D from the slits to the screen. You can do the same job, except that the range of integral, the lower and upper limit of the integrals are shifted from 0 to A. This is the single slit experiment. And the double slit, we have to add one more piece that has been translated by small d. This one is the previous result, and we just do the same job after translating x by d. As a result, we have the same small phi that is determined by the ratio of a single aperture size divided by the wavelengths, and we have additional phase difference coming from this d. And we call this capital phi to be the same as a small phi, except that A is replaced with small d. Again, we have the very same factor. In addition, additional factor due to phi, we know these two, sum of these two will always give the factor cosine 2 times cosine half of phase difference. This rule is applied to we have additional factor. And we know small d is much greater than a. Okay, that's quite important. And as a result, the double slit experiment will give this kind of shape. Because the d is greater than a, that means if we substitute this one into an argument, this magnification makes this oscillation very fast. So the period of this should be very tiny in comparison with the period of this distribution. Sure, only in the numerator. This total factor is not periodic anymore. However, as far as this part and this part is concerned, both of them are periodic. And the period of this is very tiny, and period of this is very long. That means inside this distribution, this guy appears many times. As a result, the global shape of the distribution is determined by a single slit experiment. In addition, inside a single slit distribution, you will find very tiny fringes due to the separation of the two apertures, this D, because cap D is very large, the period of this is very small. Therefore, we have a very tiny oscillation due to this factor. Okay, so number of small fringes within, we call this one is envelope. Inside an envelope, we have wiggly behavior due to the separation of the two apertures. Okay, so this one, it can be magnified, and in an extreme case, distance d is very large in comparison with the size A of an aperture, then the distribution does not want to die out. The whole distribution looks very flat, and then there is a wiggly behavior due to the separation B of the two slits. In practice, we introduce many slits that is called diffraction gratings. If you use diffraction gratings, then usually the envelope disappears and this envelope becomes very flat, and you will find the wiggly behavior, very flat wiggly behavior. This is the end of our analysis for the diffraction.